Hey guys, Mr. Betts here. I want to take a look at some examples of using the second version of the fundamental theorem of calculus with definite integrals, and in the context of using some different representations of problems. So in this problem, we're given information about a function and its derivative in a table. So this would be a numeric representation, and we want to evaluate this definite integral. So remember the second version or part two of the fundamental theorem of calculus says that we can evaluate a definite integral by taking the antiderivative of the integrand. The antiderivative of f prime of x would be f of x, really f of x plus c, but I'm going to choose c equals 0, and we evaluate that from 2 to 5. So that means that this is going to be equal to f of 5 minus f of 2. And then at this point, we're going to use the information that's given to us in the table. We are told that f of 5 is 12. We're told that f of 2 is 3. So this is going to be 9. Notice that in this problem, I gave you some information that you did not need. That is a very common thing. Make sure that you only use the information you need and don't use that 4 and 2 just because it's there. The second example is pretty similar, except we're just given some different pieces of information. So this definite integral right here is equal to -7. We know what f of 2 is. We want to evaluate f of 5. So I'm going to start with this one by writing out an alternate expression for this definite integral using the fundamental theorem of calculus. So we take the antiderivative of f prime and get f. So this step right here you could skip over if you're comfortable with it. So we're evaluating the antiderivative from 2 to 5. So that's going to be equal to f of 5 minus f of 2. So we know that this is -7. We know that this is 3, and we're looking for this. So I'm going to just leave that in there because we don't know what it is yet. And then to evaluate f of 5, we add 3 to both sides of the equation, and we get -4. So this is kind of taking advantage of an alternate version of this equation. So let me write that out here. And actually, I'm going to use the derivative in here. So I'm going to use this. So if I want to know the value of a function at some point, so I want to know what f of a is for some value of a, if I add f of b to both sides, it's going to be the value of the function at another point plus the integral from a to b of its derivative. This is another version. It's much more closely related to part 2 of the fundamental theorem of calculus than part 1. But this is a version of the fundamental theorem of calculus that we're going to use a lot. This is a very useful equation that we'll talk more when we get into applications. This is called the net change formula. And basically it tells us if we want to know the value of a function, we can figure out how much that function changes using this definite integral, an integral of the rate of change, and add that change to the value of the function to start with, and that gives us a final value of the function. So anyway, we should be able to do this algebraically without this version of it like I did over here. But it is a version of that fundamental theorem of calculus that we're going to use very often. This problem is very similar. I do want to point out that without this being a calculator problem, it would be an impossible problem to do. So let me write this out here. So I know f of 2, I want to find f of 5. So very similar to what we just did in that last problem. So if we evaluate the integral from 2 to 5 of f prime of x, and I'm going to replace that with sine of x squared, then that's going to be the antiderivative. So the antiderivative of f prime is f, evaluated at 5, minus the antiderivative evaluated at 2. Okay, so just rewriting exactly what I have there, f of 5 is going to equal f of 2 plus the integral from 2 to 5 of f prime sine of x squared dx. So again, this looks like that net change formula I showed you on the last problem. Well, this right here is an example of a function. In fact, it's the exact example that I gave when I said that some functions don't have closed form antiderivatives. Okay, we can't take the antiderivative of sine of x squared. It's just not possible. So we have to rely on technology sometimes to evaluate a definite integral like that. We can plug this into our calculator, which is something you should be able to do in your calculator, and use technology to help us out with this. So let me do that here. So again, we got f of 5 equals f of 2 plus the integral from 2 to 5 of sine of x squared. And so if we know that the sine of x squared is this is going to equal 3 minus, I'm going to call this, let's say I stored this in my calculator for a. So I'm just going to call that a. 3 minus a, which accurate to 3 decimal places is going to be, what is that, 2.7231 and so on, but accurate to 3 decimal places would be that. So in your calculator, you could just type in, if you store that value for a, you can just type in 3 minus a, and it's going to give you your answer.